Hello, my name is Mikhail Maslyaev, and I'd like to introduce my work on the topic of solver-based fitness function for the data-driven evolutionary discovery of partial differential equations. First of all, let's discuss the importance of machine learning in contemporary physics. Various machine learning approaches are used to solve different tasks posed by physics. You can see here some examples, but they're incredibly numerous. However, in all of these cases, we use general machine learning methods that are not specific for physics. They are often non-interpretable or they lack complexity, so they do not describe any cause effects in our systems and they give no insight about its dynamics. So what do we propose? We propose modeling some physical system using partial differential equations derived from data. In the past, these partial differential equations were derived using analytical methods, such as variational calculus and mathematical analysis, but now we propose deriving them from simply from data. So why do we choose differential equations? First of all, they are very common in physics. They can be quite easily solved using, in some cases, analytical, some cases, numerical methods. And you can compare the derived system with others just by comparing the equations that describe them. It's vital to say that our approach is not the first. There are some other ways. First of all, sparse regression has some applications for partial differential equations discovery. Here we construct a library from other derivatives when we approximate the first time derivative. So we want to make some approximation for system dynamics. The coefficients of the equations are simply the weights of our regression. This approach has incredibly low computational cost. It's just a simple regression, but it has very limited flexibility. We must construct all terms of our library manually. Next, artificial neural networks have some application for PDE discovery. Here we, just as in sparse regression, approximate first time derivative, but the differential operators are modeled by convolution operators due to some of their similarities. This approach can obtain complex nonlinear structures, but poses some limitations on the equation structures, just as the previous one. So we wanted to describe a more flexible system. For example, wave equation has no first time derivative, thus these approaches cannot model it. So how our approach works? We have some unknown system from which we can collect measurements. And looking at these measurements, we make some assumptions about the tokens or the building blocks of our equations that will be present in our result. Next, we pass both measurements and our ideas about the equation structure. They can be they can be relatively non-strict into the framework, and as the result, we obtain an equation in symbolic form where the equation is represented as a sum of the equation terms containing derivatives and other functions. Now let's discuss how the discovery of the equation is done. During the preprocessing, the data is denoised using kernel smoothing or an artificial neural networks or fully connected feed to represent the data. Next, the derivatives are calculated using differentiation of fitted polynomials or some finite difference scheme. And from this input data, we create first a random set of equations that are altered during the equation search. And here you can see that both mutation and crossover operators are applied. We will discuss them later. But the main question of our research is the selection of such fitness function that will guarantee the best convergence of our algorithm, both in terms of time and reliability. Now let's briefly discuss how the evolutionary operators work. So we have both mutation and crossover. Mutation is the random alteration in the term equation structure. It can be done by changing some factors in our terms to another ones, or by entire term change, where the new term replaces the previous one. The crossover is held by exchange of factors between parent equations. There are some limitations. For example, terms with we can have similar terms in two equations, and in this case they exchange only function parameters, like trigonometric functions frequency or powers. Now let's discuss the question of fitness function. So how we evaluate the quality of the proposed equation. The first approach is using the partial differential equation solver. We just simply solve the equation proposed by our algorithm. However, this approach can be relatively difficult because the structure of the proposed equation is specifically arbitrary because of our research, and all of the conventional numerical solving methods require knowing differential operations beforehand. So we must so these methods cannot be applied, and we have developed a new novel technique of partial differential equation solving that can work on an arbitrary, but it must be correctly opposed differential operator, and it must be supported by some initial and boundary condition from data. Here we use only Dirichlet type boundary condition because the values of derivatives on boundary of the domain tend to be relatively high due to numerical errors. So we state the problem of equation solving as an optimization problem. We minimize the error of differential operator and boundary conditions. And the optimization is held in Sobolev space, and as you can see, we must select such function u that has the minimal value of the error. The differential operators are substituted by their finite difference equivalent because we cannot operate with continuous data in our process due to the numerical representation of process. And here you can see example of the first time derivative that we substitute in our algorithm. On the left side is the analytical one, and on the right side is its numerical equivalent. However, the question of function search is very difficult because the space of functions is incredibly large, and thus the search will require too much resources. So we must use some parameterized functions where the optimization is held only by optimizing its parameters. The most suitable candidate is the artificial neural network, where the optimization is simply restated as the training process. And you can see here that we take the artificial neural network is used to approximate the data using the independent variables, usually time and spatial ones, as inputs. The next approach is the discrepancy-based one, which works on the idea that the sum of equation terms must be zero just by simple definition of the equation. And by minimizing this discrepancy, our algorithm may converge to the correct equation describing the process. So here we just operate in terms of identities. And fitness function calculated here is really simple. We just sum all the terms of the equation evaluated on grid, and the fitness function is the inverse value of our discrepancy. To validate our results, we used synthetic data. It has multiple advantages over using real world data, because we already know the structure of the equation, and thus we can check if our described equation is correct. The quality metric here is the success rate, the number of successful runs when the algorithm converges to the true equation with small numerical errors in coefficient values, in most cases due to numerical errors. And for validation, we use Korteweg-de-Vries equation, which you can see here, and the correct and the stated initial and boundary conditions. Algorithm was held on 10 different noise levels, where for each noise level there were 20 independent branches, and we have checked the convergence there. We can see that algorithm on low noise data tend to converge in both cases. Then with higher errors, only the solver-based approach is able to reliably get correct equations. And on very high noise level, algorithm in any cases lose the grip on the equation structure. The output of our equation is the Pareto frontier of equations describing the data, and you can see here on the example that the desired Korteweg-de-Vries equation is on this frontier. So we can make conclusions that both approaches work. For our task, that the solver-based approach requires more computational resources due to the necessity to solve equation on each evolutionary step for each proposed candidate. It can get better convergence, but we must take into account this trade-off between time and reliability. So the selection of fitness function can be task-specific, and if the high noise values are expected, we shall use a solver-based approach, while on clear data, the simple discrepancy-based approach can be used. It's important to say that in a real-world application, in most cases, the noise is relatively high due to sensor errors, so the solver-based approach is more preferable. In the future, we want to, first of all, improve our partial differential equation solving algorithm. It requires high computational resources, but there can be some workarounds to reduce it. And next, we want to try our technique for discovering of ordinary differential equations.